So the other section that we'll cover in this module is limits at infinity. That's section 2.7, which is limits at infinity. So this is about studying the asymptotic behavior of functions. As x approaches either minus infinity or plus infinity. So at both ends of the real line. Here, x going to infinity refers to, in case you have forgotten, that to a situation where x increases without down and the same way we say that x is going to minus infinity when x is decreasing without bound from below. Now, again, we recall the formal notion of what it means for something to have a limit as x approaches infinity. So the limit of f of x as x approaches infinity will be equal to L if, this is very informal, f of x gets closer and closer to L as x gets larger and larger. In reality, f of x needs not be getting closer and closer. Eventually, yes. So the idea is that if f is converting to L, you can find a very large value R, such that beyond that f of x lies within a very narrow neighborhood of L. So the images of f are trapped between very small neighborhoods of L. So L minus epsilon, L plus epsilon. So no matter how small the epsilon, you can always find a large number R, such that the images of f will be in between L minus epsilon and L plus epsilon. So something like this. Let me write down. So we say that the limit at infinity is some number L. The function may be oscillating, but it's eventually trapped within smaller and smaller neighborhoods of L. Okay, so that's the notion of convergence at infinity. And now, if a function first of all need not have a limit at infinity. If you think of f of x equals x, equals x does not have the limit at infinity. As x goes to infinity, f of x, which is equal to x, goes to infinity as well. So there's no number L, such that f of x approaches that number. So not all functions have a limit at infinity. When a function does have a limit at infinity, y equals L, so the constant function y equals L is called a horizontal asymptote. Okay, and we have similar definitions for the situation when we let x go to minus infinity. Okay, now one example here is, say, the limit of e to the x as x approaches infinity, well, does not exist, and in fact this is equal to plus infinity, while the limit of e to the x as x approaches minus infinity exists as it's equal to 0. If you remember the graph of e to the x, well, this is 1, so e to the x, e to the 0 is equal to 1. And so it has an asymptote to the left, so e to the x is approaching 0 as x approaches minus infinity, and increases without bound as x goes to plus infinity. And so those are elementary examples. F of x equals x, where you don't have any kind of limit at either end of the real line, and also e to the x, where it becomes unbounded on one side and goes to 0 on the other. Now, what are we gonna do now? Oh, what we're going to do now is to apply the notion of limit at infinity to see the behavior of functions when x becomes very large. And for that, I mean, we're basically dealing with rational expressions, so polynomials over polynomials, but this is not the only thing we'll apply this principle to. We will need to record, however, some limits that we'll use over and over. And that's our first theorem. For Ln greater than 0, the limit of x to the n when n approaches infinity, or n goes to infinity, sorry, is equal to infinity, while the limit of x to the minus n when x goes to infinity, which is the same thing as the limit when x goes to infinity of 1 over x to the n is 0. Okay, so this is one thing that we'll need to use. So x to the n always goes to infinity when n is positive, and I'm sorry, here this should be x, and when x goes to infinity, and 1 over x to the n goes to 0 when x goes to infinity. Now, if n is a positive whole number, we can also ask ourselves what happens when x goes to the other end of the real line, so x goes to minus infinity. And two things can happen depending on whether n is even or odd. So it goes to plus infinity if n is even. Then the most basic example that comes to mind is when n is equal to 2, so you have x squared. No matter whether you go to the right or to the left, x squared goes to infinity. But if it's odd, then x cubed, for instance, goes to minus infinity. Also, x to the 1, which is equal to x. If x goes to minus infinity, then we're already saying it. We're already saying that x goes to minus infinity, so x, of course, goes to minus infinity. X to the 1 goes to minus infinity. So in this way, we have a very clear picture. So when x goes to infinity, x to the n goes to infinity, and x to the minus n goes to 0. When x goes to minus infinity, however, we need to consider a positive whole number. Otherwise, we'll be taking root of a negative number, which is not allowed. But then we can say that either it goes to plus infinity if n is even, or to minus infinity if n is odd. So x squared, x to the fourth, and so forth, they all go to plus infinity when x goes to minus infinity, but x cubed, x to the fifth, they all go to minus infinity when x goes to minus infinity. We can also ask what happens when we have negative powers. We still need to restrict ourselves to positive whole numbers. Otherwise, we'll be taking, as I said, we will be taking roots of negative numbers, which is not allowed. But this is what you would expect, and it's the same thing that happens on the positive side. We're dividing by something that is very large. It's negative, but regardless, it's approaching 0. Okay. Also, if P and Q, so P and Q are positive integers, the limit of x to the p over x approaches minus infinity will be equal to minus infinity if q is odd and will not be defined if q is even. So think again of the case when q is 2, so that's an even number, and piece 1, you'll be taking the square root of a negative number and then sending an x to minus infinity. So you're taking the square root of minus 3, minus 4, minus 100, and asking yourself what is the limit of that. But then the square root of minus 4, minus 5 are not defined, at least not in the real line, or not for real numbers. Not if we restrict ourselves to just talking about real numbers. Okay, so that's not possible, so that's undefined. Okay, and there are more cases now that we need to consider. So before continuing, so whenever we are asked to raise x to any power, the real power, if you're sending x to plus infinity, you can always make sense of that, and that's going to go to infinity. The only problem is when x is negative and you're asked to take the root of the quantity x when the roots are not odd. For instance, you can always compute the cube root of minus 1, which is minus 1, but you cannot take the square root of minus 1. Also, for the same reason, even though it's not this is the remaining case that we need to talk about. If x is going to minus infinity, and if you're raising it to the irrational number, the way you usually do that is by approximating that exponent by some rational numbers. And since you always encounter both odd and even numbers, you will not be able to make sense of that. So that question, again, doesn't make sense for just general real numbers. Okay, so that basically covers everything for that, and then we'll jump into the applications of this theorem to the computation of limits at infinity of a rational function.